canceled until, actually got postponed until the end of next week. So we're going to go ahead and meet for the next 5 days or whatever, and then we'll be done. How about that? So I'm doing Washington. There's a dispute at the International Trade Commission over how to how to braze diamond, basically, for cutting tools. This is actually, I can bring one of these things up. It's a, they do different things, but the main thing are pad conditioners for polishing silicon wafers. So they make these diamond polishing things, and it's a question of how they're fighting over how they braze them. So anyway, that's that trip to Washington. Other questions? Oh, okay. Last time we were talking about heat transfer in arcs, and I pointed out there's an asymmetry in that 70% of the heat actually goes to the anode and 30% to the cathode, and then we started to relate that to why you would use which polarity for gas metal arc or gas tungsten arc, depending on whether you have a consumable electrode. You want the part you want to melt to be the anode, because that's where you're putting the maximum amount of heat, and that means in gas tungsten arc welding with a non-consumable electrode, you make your workpiece the anode, because that's what you want to melt. In gas metal arc welding, you make your base plate the anode, or you make your base plate the cathode, and you make your wire the anode, because that allows you to melt it off more quickly and fill up the groove. It turns out that in gas tungsten arc welding, you have very, very low productivity rates. Typically maybe 2 to 3 pounds of weld metal per hour that you can melt. Whereas gas metal arc welding, you can feed that wire in and you can melt it at 10, 20, 30 pounds per hour in some cases. The current in the arc carries 80 to 90% of the heat to the anode workpiece surface, and it does that because the electrons essentially go right through the boundary layer. They're not inhibited by the boundary layer. In fact, they pick up energy in the boundary layer from the anode voltage drop. We also talked about the heat of vaporization and heat of condensation of the electrons. Basically, the heat of vaporization cools off the cathode and heats up the anode, and that's what leads to the asymmetry of the heat flow. We also started talking about different shielding gases, and the 70 and 30% applied basically to argon shielded arcs, which is the most common, but it turns out if you use helium, you can get a substantial increase in the melting efficiency. And that's because we made a little table that if I had an argon arc of whatever current rating and 90% was electron heat, and 10% was convection heat, conduction plus radiation, right? That with helium, because of its higher thermal conductivity, I'd get the same electron heating because it's the same current if it had 2 arcs, but I might get, what I give you, 30% or something, a 3-fold increase. And so I get 120% or a 20% overall increase. That 20% overall increase in terms of total heat equates to a significant increase in the amount that actually gets to the workpiece, because that's the total heat that impinges on the workpiece, but a lot of it goes into preheating the base material, and only a smaller fraction goes into actually melting metal. So if only 50% of the 100% in argon goes to melting metal and the other 50% goes into the heat affected zone, going to 120% means that I actually get 20%, I get 70% melting and 50% preheating the base material for an equivalent arc and travel speed and everything else. And that means I get a 40% increase in the volume melted. Okay, 20% addition to 50% is an overall improvement of 40%. Now, it turns out, I mentioned that, or it was brought up that in Europe, they don't have, or Japan or other parts of the world, they don't have inexpensive helium. And so in some cases, they actually use hydrogen and some things you can't use hydrogen. And typically it might be a 5% hydrogen mixture. You can't use hydrogen in two cases. Ferritic steels, which are about 90% of all metals. You can use it in austenitic steels, and you can't use it in aluminum. If you use hydrogen in aluminum, when welding aluminum, you end up with Swiss cheese, because aluminum dissolves the hydrogen in the liquid, but not in the solid, and so it's the same thing as the CO2 in your soda. As soon as you pop the top on the soda, the CO2 starts coming out. Well, in solidification of aluminum, when you melt it in a hydrogen atmosphere, it soaks up about 10 times as much hydrogen as the solubility of aluminum in the solid. So as the aluminum starts to solidify, I start outgassing hydrogen, and that solidifies and traps the porosity, and you end up with Swiss cheese for your aluminum. But it turns out for austenitic stainless steels, or for copper alloys, for example, you could use an argon-hydrogen mixture. And we could go through the same type of simple little calculation we did for argon to helium ratio in terms of the thermal conductivities. If we want to do K of argon versus K of helium, the thermal conductivities, it turns out that's the square root of 4 over 40, inverse of the mass. Argon's 40 and helium's 4, and that's about factor of 3. That's why I went from 10% conduction across that boundary layer to 30%, a tripling. If I do that with hydrogen and compare it to argon, it's square root of 2 over 40, which is about 4.3 or something like that. Okay? So it turns out that I get, with even just 5% hydrogen, I'll get, well, this 5% becomes like 20%. Okay, so I get, 4.3 times 5% is, so this gives me an increase from that. But it turns out that's not the major cause. I mean, the thermal conductivity of this average gas mixture only goes up by a 20% improvement. Okay, if this is 95% and this thing is 4.3% greater, a simple rule of mixture says that I now have 95 plus 5 times 4.3, which is about roughly 120%, a 20% improvement in the thermal conductivity. Well, 20% improvement in the thermal conductivity takes this up to 12%. Big deal. That's not much of an improvement. However, there is something in a diatomic gas called the reactive thermal conductivity. And it turns out this simple, taking the inverse square root of the mass, which comes out of the kinetic theory of gases, just treats all atoms as simple little billiard balls bouncing around in the air, right? So the kinetic theory tells me that the thermal conductivity goes as the inverse square root of the atomic weight. However, if I have a diatomic gas, I can actually have a chemical reaction go on. And the chemical reaction simply being, I can dissociate the hydrogen. So if I'm up in the arc over here, and I have some hydrogen in my arc, the hydrogen is coming in from the side, from the shielding gas as it blows in. In the heat of the arc, that diatomic hydrogen is dissociated into monatomic hydrogen. Down here in the thermal boundary layer, first of all, this is dissociated because of the high temperatures. Above about 5,000 Kelvin, diatomic hydrogen splits into monatomic hydrogen, and there's a heat of dissociation. Okay? It takes energy to break the bond. And I have to get to 5,000 degrees, so it's a fair amount of energy to break that bond. However, when I get back down in this boundary layer, which may be in the 3,000 degree range, those two hydrogens up here recombine to form diatomic hydrogen. And they give up the heat of dissociation. They give it back. And so if you plot the thermal conductivity versus temperature of a diatomic gas, and we're talking in thousands of degrees Kelvin, you'll find some kind of plot that looks like that, okay? This is the temperature range, maybe 3,000 Kelvin, if this is thousands of Kelvin, okay? Up here, I'm monatomic. Down here, I'm diatomic. And in here, I'm reacting and carrying the heat of dissociation. And so it appears that I have a very high thermal conductivity because the material I have is recombining and giving up all that extra energy in that temperature range, which just happens to be the temperature range of this gravity layer. And that's true of not just, you doing okay? Oh, drop the mic. You're going to have to get another.
I'm really sorry. I'll work on it.
This guy's the World Trade Center talk. Stole our clip. Anyway, in any case, you get that energy that you put in up here back down here, right where you want it. And it's not just with hydrogen, but coming back over here, you get with just 5% hydrogen because of the reactive thermal conductivity. There's not a simple way to calculate this, but with just 5% hydrogen, you can get a substantial increase. And I'll just say it's 30%. I can't calculate it for you. I just throw it up there and wave my hands, right? But 5% hydrogen in argon will substantially increase the heat transfer to the surface. Now, it's not just hydrogen. If I weld with carbon dioxide will react in the plasma, dissociate up here to carbon monoxide and oxygen. And then down here it will recombine. So it turns out we actually do gas metal arc welding of steel with carbon dioxide. And in fact, if you look at the arc, you'll see a very central core, which is it just even looks hotter. You have to look at it through a filter, obviously. But you look at a CO2 arc as opposed to an argon arc. An argon arc is hot in the center. It just kind of tapers off in its luminosity, right, as you go out radially from it. A CO2 arc, on the other hand, will have a hot central core, and basically what you're seeing is as you go out radially, you're seeing this big spike in the thermal conductivity that kind of gives a boundary there, okay, where these two things are recombining. And so you have a kind of a jump. You don't have a simple decrease in temperature as you go across. You actually you get a spike in temperature. Actually, not a spike. You get a flattening out at one spot, which tends to give you a hot core. And because of that, I'm not going to go into all the reasons or all the consequences of that, but CO2 arcs behave differently than argon arcs. And if I go into gas metal arc welding and I'm using argon to weld with, I can have a nice uniform arc and I can do all my arc physics. If I add 5% CO2, things aren't too bad, but if I go to 50% CO2 or even 100% CO2, the arc characteristics change dramatically. And I start getting very narrow arcs that have these hot cores. And we'll talk a little bit later about plasma jets and how this creates a stiff arc and throws spatter around and things like that. But it changes the physics of what's going on. It turns out helium with its higher thermal conductivity does a little bit of that too. So this is a reactive thermal conductivity. This is inherently lightweight molecule or atom conductivity, but higher thermal conductivities in the plasma tend to give shorter or narrower arcs with higher heat intensity in the center. Okay, so that's something about shielding gases. By the way, you won't find that anywhere in the literature. That's kind of things I've deduced. In fact, what you'll find in the welding literature is all kinds of gobbledygook that means nothing if you think about it very hard. I mean, if a good plasma physicist read what the welding folks, the welding physicists, or the welding engineers say about plasma physics, they would just laugh, okay? This is one area where the welding handbook is about 80 years out of date. They just have never thought about things very hard. Okay. Well, you use different shielding gases for different reasons, and maybe I ought to go through that a little bit. If I'm welding something that's very reactive, like titanium or aluminum, I have to use 100% argon. I can use an argon-helium mixture. I can't use hydrogen, and it turns out for aluminum, I can't use CO2 because aluminum would react. It forms a very stable aluminum carbide and a very stable aluminum oxide, so it'll just react with the CO2. So you can't use CO2. It turns out when welding steel, most commonly, we end up using an argon oxygen or argon CO2 mixture. So for aluminum, you're going to use pure argon or helium or argon helium mixtures for your plasma gas. For stainless steel, you can use argon with, well, actually, let's do steel first before I get to stainless steel. For carbon and low alloy steel, which is most of the metals, I use something like argon 1 to 2% oxygen, or argon 5 to 20% CO2, or 100% CO2, or helium, or mixtures of argon, helium, CO2. This one of these is called L75, Lindy 75, is an argon, helium, CO2 that was mixtures. It was patented originally, but the patents run out. And then there's something called argon. That's an argon, helium, CO2 oxygen mixture, which is called time gas, thermally ionized molten energy. It's a bogus patent that's about 15 years old. Instead of paying $60 a bottle for your argon or argon oxygen, this guy from Canada has been selling the U.S. Army bottles at $300 a pop. There is no difference between time gas and what Lindy developed. He just got his patent by putting a 0.5% oxygen in this. You can prove that it makes no difference whatsoever. You can read the patent and find that the whole thing is bogus. He pulled the wool over the patent examiner's eyes, but he's made a fortune off of it. It's just as good as vibratory stress relief, which is one of the biggest frauds ever perpetrated on the welding industry. Okay, there's a company that still goes around selling vibratory stress relief equipment. This is, instead of doing mechanical or a thermal stress relief, they say if you just vibrate the part for a few days, shake it up, okay, it'll stress relieve, Well, maybe that's, how this guy stress relieves himself, but it's not how you do it with metal. So time gas is, I can't believe the U.S. Army builds tanks with this stuff, but someone sold some idiot at General Dynamics Lima tank plant on this. It's probably money under the table or something. That's unofficial. That's just, it is one of the stupidest things going. You might as well burn your money. Actually, anyway, why do I use all these different things? It turns out if you try to use pure argon with carbon steel, the arc's not completely stable. It'll leave a rough weld bead. If you add just a little bit of oxygen, it seems to run smoother. In fact, you can hear the arc. It just kind of, it is a smoother sounding arc. It doesn't have little crackles and pops and stuff. CO2 will do the same thing because CO2 just adds a little oxygen to the shielding gas, and CO doesn't oxidize steel weld metal. Okay, you're adding a little bit of oxygen to the shielding gas. We don't really know. No one's ever quite figured out exactly what it does to the arc behavior in terms of helping to stabilize it. We do know that you can add other things to the arc to stabilize it, and they often do in fluxes. Things like in the flux, if you add lithium or barium or strontium, turns out these are in the first column of the periodic table, and it's easy for them to donate electrons. It's easy to strip an electron off those atoms, and that tends to give me easier arc starting. This is actually easier arc running straight DC, which is a little bit different. And there is no good theory about all this. If you want, I could give you a little bit of theory. It has to do with cathode spots and anode spots, but we'd have to spend a day talking about what cathode spots and anode spots are. But it's only a hypothesis. It hasn't been proven. If you're using helium, you'd also use you might put some oxygen in there. In any case, use all kinds of different things for steels. The problem with 100% CO2 or with lots of helium is you start getting more spatter. In fact, in a 100% CO2 arc, hey, now you're talking a cheap gas. I mean, this is a greenhouse. People are trying to get rid of this gas, right? It's all over the world. So you can buy bottles of this stuff for $2 or $3 a cylinder as opposed to $50 a cylinder or whatever it is. So for argon. So this is a very, very cheap gas. They love to use it in the automotive industry where they're trying to cut costs all the time. The problem is that you get spatter all over the place. Okay, spatter is just molten drops that end up solidifying on your workpiece. And if you're in a non-cosmetic situation, it's no big deal. If you're in a cosmetic situation, like an automobile, it turns out you have to come along and grind it, and there's all kinds of problems with that. In general, there is an oxidation that goes on with 100% CO2 because 50% of your atmosphere is going to be oxygen. You can tolerate 5% oxygen in your atmosphere, but 50%, you're going to start to oxidize your steel. It turns out the welding electrodes here a welding electrode in carbon low alloy steel for these shielding gases might have 1.5% manganese and 0.5% silicon in the electrode. And you'll oxidize some of that away, but you end up with 1% manganese and 0.25% silicon in your final deposit. In order to do that here, you've got to start with 2.5% manganese and up to 1% silicon in order to get that same deposit chemistry, because all that extra oxygen is oxidizing away some of your alloying elements. And certain types of steels that might have a little bit of titanium or niobium in them or something like that for a beneficial effect, if you try to weld it with this, you won't get any recovery of that alloying element in the metal. So there's lots of weld metal chemistry. This is why we train welding engineers, to study all the nuances of this. It could be a whole course if you wanted to really sleep. Yeah. Well, there's all the cleaning rework, and that's why the savings does not pay for cleaning off the spatter. If you're inside a building and you're going to cover everything with not asbestos, but insulation afterwards, who cares? You know, if you got some spatter on your beam, no one's ever going to see it. If you're talking an automobile, you can't tolerate it. If you're talking a high toughness deposit for a submarine or something, you can't use this because the oxidation is going to leave all kinds of inclusions and lower quality, lower toughness in the weld metal. Okay, you're talking sheet metal though, or structural steel beams that are going to be hidden inside a building. Who cares? You can use the cheap stuff, and you don't need fantastic properties. You just need adequate properties. But if you're going for the best properties or you're going for the best appearance, then you're going to use the more expensive gas. And I'd say, well, it really depends on the industry. But if you look across the whole thing, half the industry uses the expensive gas and half the industry uses the cheap gas. But it really is, it is both properties and economics. Okay? The cheap stuff, lower properties, but at a savings, right? If you want a really high quality deposit, you go with 100% argon. Now, if I go to nickel-based alloys, it turns out they use argon or argon with 1 to 2% oxygen. Oops. This stabilizes the arc. It makes a nice looking bead, but it also oxidizes the top of the bead with nickel oxide. And you have to go in there, and if you're doing multi-pass deposits, you got to grind the surface before you put the next bead on. Well, if you've ever been to Electric Boat, where they weld a lot of nickel-based alloys, Inconels and Monels and stuff, they use this. It's great if you got a single-pass weld, but if you got a heavy section and a multi-pass weld, and sometimes you're better with this. The problem with this is those non-uniform weld beads sometimes lead to lack of fusion defects. And so you've got a trade-off, and no one's really quite decided which one's more economical. It's a question of how much it costs you to fix those defects. Because both of them, this produces oxidation defects, and this produces defects of lack of fusion. And so it's just a question of how do you want to control it. If you're going to stainless steels, turns out you can use argon oxygen, you can use argon hydrogen oxygen, and essentially almost everything else you use over here for carbon and low alloy steels. If you're talking austenitic stainless steels. If you're talking ferritic stainless steels, you can't use, so this is really austenitic stainless steels. And you can talk about titanium. It's very reactive. You got to use argon or helium, so far as that goes. And it's shielding gas. Okay? Does that answer your question? So there's a certain art to, but there are scientific principles, but there's still a certain art to selecting the right shielding gas. And that's where you really need someone who, I mean, I can't give you rules, simple rules, just this is what you use. You really need someone who's got some experience, because you're getting into the arc operability. And that's a very, very subjective thing. Okay? Yeah. Yeah, yeah. You can always use argon. It may not give you the most stable arc, and it may not give you the best looking bead, but if you can do arc welding on it, argon's going to be as good as anything, and reasonably cost at a reasonable cost. I mean, a tank of gas can run you can run for 3/4 of a day on one tank of gas for $50. So you're talking $10 an hour worth of gas at high productivity rates. Who cares? You know, big deal. You know, your total burdened cost to have a person welding and everything is probably more like $75 an hour. You know, and so yeah, you could knock $5 an hour off that or $7 an hour off that if you use 100% CO2, but the quality goes down. And then you have to, if you can't afford to go in there and start spending an extra hour to clean all the spatter off. So you can see why you can't afford to clean the spatter off if you run some of these types of numbers. I mean, people realize where, I just kind of threw those numbers out because I just made them up in my head, but they're not completely made up. I mean, what's a welder cost you to employ him per hour? 30 or 40 bucks an hour. How do you get that? Someone works for 2,000 hours a year. You're going to pay them $40,000 or $35,000 or whatever if you're in some sort of union shop. And then you got the overhead and the burden, which is going to be 70% on that or something. So you got 75 bucks. You got 75. Well, that's only 75,000 a year. But then you got just the general overhead and maintenance and supervision and everything. You got 100% burden on top of that. Okay, you got the benefits. If you go from 40 bucks an hour and add 70% for benefits and health and everything else, you're up to 75 bucks an hour. And then if you got supervision and overhead and the equipment and everything else, you just say double that, you get 150 bucks. How am I doing all this? Anyway, you can get to $150,000 a year. Okay, it's basically what it's going to cost you for most employees. And in fact, I once went through with a LFM student working at Boeing. He worked at the Door Product Center. And this is a very interesting manufacturing operation, and they know exactly how many doors they have to build for aircraft. Because you know exactly how many aircraft. I mean, the aircraft is this $100 million thing, and you just have to build a door. And you know how many doors are in the aircraft, and you know it 3 years ahead of time. It only takes you about 1 year to build these things. This is a deterministic manufacturing. There's no uncertainty in how many doors you have to build each year. Well, it turns out, I said, as we were going through and we were watching all this, I said, well, how many doors do you build a year? And it turns out they build about 750 doors a year. Now, some of them are great big doors for the freighters, the UPS freighters or whatever, and so the door is like the size of a garage door. And some of them are the doors that you walk through when you board a plane. And some of them are the emergency doors that are even smaller, but total they build, you know, you figure out how many planes they build, and there's 5 doors or 6 doors or whatever on each aircraft, 8 doors on some, and they build about 750 doors a year. Well, the Door Product Center employed 250 people. Anyway, I said, well, I happened to say, what's the value of a door? I mean, I just kind of like to know the value of the product so I can estimate what kind of leeway you have in terms of processing, you know, what you can afford to do. And they said, well, we don't know. They'd never calculated it. And anyway, so in the conversation, I came up with these 2 numbers, 750 doors, 250 people. And I told the manager of the plant, I said, when I asked him how much a door cost, actually later I came back, I said, well, I figured out how much a door costs. He says, what do you mean? It costs you $50,000 for a door. Why? Because each person is $150,000. You got 250 people with all your overhead and burden and everything else. You can take almost any manufacturing plant you want. It's $150,000 a person per year. That's for their salaries and the overhead and the supervision and equipment and the heat and the light, everything. And you won't be very far off. You might be 25,000 off, but who cares, right? And you make 750 doors. And I figured it out. I divided 3 into 150 and I got 50. Okay? And he thought about it. I mean, they actually, when they had tried to estimate, some of his underlings had tried to estimate, oh, well, maybe it cost us $15,000. They didn't have the foggiest idea of what it cost to build a door. They just knew they had to build doors. Okay? And they had never stopped to even think what the value of the product was. So, but how could you not do that? I mean, if you're going to try to say, well, how could I change something? I want to know what the value of the change is going to be, right? And they didn't have the foggiest idea. But, you know, of course, I was averaging in great big doors with little emergency doors. But nonetheless, you know, if you just take the regular old door you walk through, it's about a $50,000 door. Okay? But not very many people replace just a door on an aircraft. I mean, you don't have a lot of collisions that you only have to replace the door. But nonetheless, getting back to this welding thing, if it's $150,000 a year, that's $75 per hour for the welder. Okay? So if it's $75 an hour for the welder, and I use $10 worth of argon, that's $10 of that 75 of running that plant and having the welder work is paying for the argon. Now I might be using 30 pounds of weld wire well, actually, let's say I'm using 10 pounds of weld wire. That's probably more typical for a manual welder. And that could be anywhere from $1 a pound to $3 a pound. So actually, that cost of that stuff may be actually getting above that. But the basic person burden cost is something on $75 an hour. And you know it's something like that because you go get your car fixed. It's going to be $45 an hour, or the plumber that comes to your house to fix something costs $60 an hour, or whatever. Okay, that's just what it costs to do anything with basic needs. So, okay, you ought to run some of those numbers in sometime. It's helpful to well, that's actually basically just what engineering is being able to estimate things reasonably precisely. You don't have to be, you know, so super precise in most cases that you're within 1 or 2%. You just have to be in the ballpark. Most people have never even run the numbers and they're off by a factor of 5, just like these guys at the Door Product Center. They were off by a factor of 3 in guessing what the door was worth. That was their business, you know. Okay, I was going to talk about arc ignition, which I like to talk about only because if you're going to run a robotic welding system, you have to start the arc. And because I like to slam the American Welding Society and the welding handbook on the physics of what's going on. Turns out, if you read the welding handbook, it will tell you that the way you start an arc is, one of them is Paschen breakdown. Paschen breakdown goes back 120 years to when people first had electrical power supplies, and people would find that if you take 2 electrodes and apply a voltage to them, and bring them very, very close together, as close as you possibly can without their touching, you get down to something less than a tenth of a millimeter, kind of a human hair distance, and all of a sudden an arc would start. If you had thousands of volts. If I have a 1,000-volt potential and I bring these things within a human hair distance, bingo, an arc would start between the two. Well, that's a nice theory, except the open circuit voltage on a welding power supply is typically about 80 volts. Where do I get thousands of volts? You don't. Passion breakdown has nothing to do with anything in welding, starting of a welding arc. Except it's in the welding handbook, that's the only thing that has to do with it, okay? Next they tell you, oh, we have field emission. What is field emission? Well, field emission comes from the 1920s, where people, all these physicists were starting to study vacuum arcs and things, and I told you it's a very complex subject to understand how the electrons get out of the cathode. And in fact, I put up this plot the other day, and in this plot, this is the energy level of the electrons, the Fermi energy down here, this is the work function, and this is the solid material on this side of the vertical line. This is a solid material over here, the Fermi energy. This is the potential well that the electrons sit in the air just in front of it. So this is the surface right here. This vertical line is the surface between the solid and the gas, or the solid and the vacuum. And to get the electron out of the solid, you have to apply the work function voltage in order to make it a free electron up here at zero of energy. Well, that's basically called a potential well, and the electron sits down at the bottom of the well. I can lower the sides of the well by applying an electric field to the surface. Essentially, I take that potential well and I just bend down the sides because I'm applying a voltage gradient, an electric field here. And now in the 1920s, people start talking about quantum mechanical tunneling through that potential barrier. Because in the 1920s, when they studied quantum mechanics, 30 years ago in this room when I studied quantum mechanics, they teach you that you don't have to go over, you can go through if it's thin enough, and the height is low enough, but it's also thin enough, you can tunnel through it. So field emission was something that they started to understand in the 1920s and 30s. It turns out all you need for field emission is about 10 to the 8th volts per centimeter. Okay? Well, that's a lot of voltage. Now, it turns out, I told you before, if I went down to, let's say in Paschen breakdown, I went down to 0.1 millimeters, and I had 10,000 volts. Okay? Well, that's 10 to the 4th volts divided by 10 to the minus 2 centimeters is 10 to the 6th volts per centimeter is what people were measuring for Paschen breakdown. Okay? I said it took thousands of volts, 10,000 volts over a tenth of a millimeter. It's a little bit thicker than a human hair. Well, that's not, you'd say that's not field emission, but aha, it is. It turns out Paschen breakdown in the 1880s was the same as field emission later because I have these little asperities on the surface. And what happens if I have a little asperity on the surface in terms of voltage? I get a concentration of voltage around those points. And if you take something that has a field of 10 to the 6 volts per centimeter, right here at some little asperity on the surface, I can have 10 to the 8th. And I'll get breakdown. I essentially am getting field. Paschen breakdown was just an 1880s version of field emission. At 10 to the 8th volts per centimeter, I actually lower that barrier enough, I actually do get tunneling of electrons right out of my metal into free space. But Paschen breakdown was just an example of that, but you still need thousands of volts. So again, the welding handbook is wrong. Okay? Now, it turns out we know, just to let you know, it turns out that if this was a liquid metal, it turns out I don't need 10,000 volts, I need 100,000 volts. Why? Because the liquid metal surface is smooth. There's no sharp peaks. It turns out you don't really need quite 10 to the 8th because you get that strong electric field, and even the liquid will now start to distort under the field. Okay, and so you will get little spikes, not as sharp, about 10 times less sharp. And so you have, but you still have a slight concentration. It still takes 10 to the 8th volts. So your field emission on a liquid surface is even harder than it is on a solid surface because the liquid metal is smoother. Okay, so we've now talked about the two things that are in the welding handbook that actually don't start arcs. And then you say, well, what does start an arc? Well, the welding handbook says, well, you can touch start. And they don't tell you anything about it. What's touch start? Well, touch start, I just take the welding electrode. Anybody ever, how many people have ever welded stick electrode? Okay. Oh, how do you start? You come in and you just touch it, right? The tip of the electrode, I didn't bring my electrodes today, but the tip of the electrode has got the flux ground off, so that you've got bare metal, so you just touch the bare metal to the surface and pull it away, and voila, the arc starts. There's only 80 open circuit volts. In fact, most power supplies, when you first touch, they drop down to maybe 10 volts in some cases. I mean, they're designed that way. Because you don't want 80 volts with a dead short. Because then, in fact, when you first started learning weld, you did that. You can't pull it, trying to pull it up, you know, right? You welded your electrode to the plate, right? I've done it. Most of you have done it, right? Okay, if you've ever welded. So yeah, it's got to be a very gentle touch start. Well, even though they don't bother to tell you, it turns out Ragnar Holm told us what happens. And Ragnar Holm was one of these great German scientists of World War II that we took out of Germany after World War II and brought back to the United States. In this case, he went to work for Westinghouse. And this is Electrical Contacts by Ragnar Holm, 4th edition. If you look on the inside, and this is for all you people who like to look at the history of gender in the United States, it says Electrical Contacts Theory and Application by Ragnar Holm in collaboration in small print with Elsie Holm, his wife. Okay, not exactly equal billing back in 1946 from the German, but. In any case, Ragnar and Elsie were actually a scientific pair, but Ragnar got all the credit. In fact, today, the IEEE, the electrical engineers, annually have the Holm. It's called the Holm Conference because he was such an expert. I mean, he was decades ahead of everybody else in understanding electrical contacts. So in here, Ragnar, pardon me? It may have been, okay? It says, in collaboration, it says Ragnar Holm, PhD, okay? In collaboration with Elsie Holm, PhD, but in fine print, both of St. Mary's, Pennsylvania. Okay? Anyway, I always thought it was sort of interesting. So Ragnar Holm, in Electrical Contacts, teaches us that if I have two surfaces, this is an asperity and this is an asperity. Okay, I'm going to model them as trapezoids. So this is solid material, right? And this is solid material down here. And I'm going to apply a voltage of minus V0 over 2 and plus V0 over 2. So I have a voltage of V0 across this asperity contact. I'm going to generate resistive heating by flowing a current through here. I'll just call it capital I right now. And that heating at that interface is going to cause heat to flow away, and I have to solve Laplace's equation to figure out what this is at steady state. Okay? It turns out, if I want to know what the both voltage isopotentials are, I also have to solve Laplace's equation. It turns out the same equation with just different numbers in there. If I want to know what the isopotentials are, they look like that. If I want to know what the isotherms are, they look exactly the same, just a different scaling constant. And without solving the differential equation, because I only solved one differential equation in this class, but if you want, Ragnar already solved it. It's in the book. But you end up integrating the thermal conductivity. This is just heat flow times the electrical resistivity dt from T to T. T theta is, he does this dimensionless, okay, or T infinity you can call it, okay. And you do this from 0 to V0 over 2 of V dV. Turns out this L, this Kp, the thermal conductivity times electrical resistivity for metals is roughly a constant. As the thermal conductivity goes up, the electrical resistivity goes down. Copper has high thermal conductivity, low electrical resistivity. Okay, it turns out it's called the Wiedemann Franz Law. And so it turns out the Wiedemann Franz Law says this quantity is equal to L times T, so I got T dt and V dV. And it turns out you end up with 1.2 times 10 to the 8th, 10 to the minus 8, T infinity squared minus T0 squared is equal to V0 squared over 8. And if you now go through, it now tells you that the temperature at this interface is proportional to the voltage. And if I go through, this is in units of Kelvin, volts, and yeah, volts squared for a degree Kelvin squared, okay. It turns out the melting voltage for aluminum melts at 660 C. To get to 660 C right here, you need 3/10 of a volt applied across here to melt that asperity. To copper, you need 0.43 volts. And for to boil copper, you only need 0.8 volts. For tungsten, you need 1.1 volts to melt and 2.1 volts to boil. Very low voltages create tremendous temperatures at these asperity contacts. And table 10 in Ragnar's book is a table of melting and boiling voltages for electrical contacts. Yeah. It doesn't matter what the current is. The current drops out. Yep. If you have a 9-volt battery, there will be some little, and you go in there, if you break the contact on a 9-volt battery, and you go in and look carefully enough, you will find a slightly melted contact somewhere. I mean, you may take you half a lifetime looking at a scanning electron microscope, but there will be a little spark there. Now you say, well, why didn't that spark blow up things? Because it doesn't matter what you're talking about. Well, even if you're talking nitroglycerin, the spark energy has to be above some certain threshold. And it turns out these things, we're talking minute things here. But in terms of starting a plasma, you only need a minute thing, okay? You basically, when you touch start, when you pull off, when you break that thing loose, there's enough inductance that you basically start a micro arc right there. As long as you have, I take this back, as long as you have, you can't do it with 1.5 volt battery. And the reason is you can't sustain an arc with less than about 6 volts. That's the anode and cathode voltage drop. I would not advise you to take a 9-volt battery and stick it to your tongue, okay? In both electrodes, huh? Too late, you've already done it? And how's it feel? It tingles your tongue, okay? Well, it turns out you actually can get a spark with a 9-volt battery. You definitely will get one with 24-volt battery. It depends on what the electrode materials are on a 9-volt battery. In fact, I usually say it takes about 10 volts to get an arc, although if I'm really trying to be very conservative, I say you only need 5 volts to get an arc. You cannot get an arc at 1 volt. You just cannot get an arc because you don't have enough voltage for the anode voltage drop and the cathode voltage drop. Okay, remember If you got to have those voltage drops. Who cares about the plasma column? You don't have enough voltage unless you've got somewhere between 5 and 10 volts. At 24 volts or anything like that, you've got plenty of voltage. And so in a welding power supply, 80 open circuit volts, you can come down, and even if it drops to 30 volts or 20 volts, you'd be able to get an arc. Actually, when they drop down to 10 volts, it's harder to get an arc. That's just what they call. That's when they drop down sometimes to 10 volts just to let you know by electrical contact resistance that you've touched. Okay, because I said you need to know this because of robotic welding. How do you start an arc with a robot? Well, the robot has to feed the wire in until it touches. Well, robots are not very sensitive, right? They don't slow down. They don't see that they're coming in, and they've got to stop soon and change their velocity. They just go wham, right? And then you bend your wire and you can't start anything, right? So it turns out typically you'll feed in slowly and you'll have a chisel tip, and they may have a search voltage of 5 or 10 volts, which won't start an arc. And then they will, once you say you tell the machine you now want to start the arc, it's just barely touching, and now it raises the voltage up to 30 volts or 40 volts or 80 volts, and now it breaks the circuit and starts the arc. So even in automatic machines, it's basically touch start is one of only 2 ways that we can start arcs. The other way we can start arcs is high frequency, and that's basically just a Tesla coil. If I put a 100 kilohertz oscillation frequency on something, a Tesla coil will, you hold it up to a fluorescent light, just hold it next to a fluorescent light, and it will cause the gas to discharge inside. Okay, you're basically creating a plasma by high frequency. You're basically shaking the electrons off in that case, okay? Not vibratory stress relief, but you can shake the electrons off at a high enough frequency, okay? Actually, it's resonance. Yeah. Yep. You're just getting a high frequency oscillating magnetic field will resonate the electrons off, some of the electrons off the atom. Once you've got free electrons, the plasma, if you've got a voltage across there, the plasma opens up. So the 2 things we actually use are the 2 things they hardly talk about in the welding handbook. The 2 things they spend all the time on don't apply. So touch start is used all the time, and high frequency overlay is sometimes used to start welding arcs. It's not a trivial problem if you start thinking about how the robot has to learn how to come in and do a very gentle touch. And typically you also have to have a chisel tip. And next time we'll talk about how you get a chisel tip on the end of your electrode. Okay? How a robot does that. You do it by just cutting it.